In this video, we're going to introduce capacitance and look at different ways of combining capacitors. If we look at a capacitor, each plate will be charged until it has equal but opposite charge Q on each plate. Because of this separation of charge, each plate will be at a different potential, so there is a potential difference or voltage between the plates. This potential difference is proportional to the charge on the plates. If we double the amount of charge on each plate, we will double the potential difference between them. This means we can write the charge equal to a number we'll call C times the potential difference. This number C is our proportionality constant, and we will define it to be the capacitance of the capacitor. Rearranging, we can write the capacitance as the charge divided by the potential difference. The capacitance is the charge per volt stored on the capacitor. The unit of capacitance is a farad, named after Michael Faraday, and 1 farad is equal to 1 coulomb per volt. The capacitance is a property of the physical capacitor, and we can show this. We know the potential difference, or voltage across the whole capacitor, is the electric field times the plate separation D. We have also found the electric field inside a capacitor using our result for the electric field of an infinite plane of charge. Combining these, we get this equation for the charge on a capacitor. Now plugging this in for the charge in the definition of capacitance, we see the potential difference will cancel, and we're left with a capacitance equal to epsilon naught times the area of the capacitor plates divided by the plate separation. Epsilon naught is a constant, and the area and plate separation are physical characteristics of the shape of the capacitor. This means we can determine or change the capacitance simply by looking at the geometry of the capacitor. This should make sense considering the definition of charge per volt. The amount of charge you can store should increase as you increase the area. And as you vary the plate separation, you vary the distance between the charges, which will affect the potential difference. Now we want to look at how we charge a capacitor in the first place. We'll first need a voltage source to move the charges onto the plates. The most common example is a battery. A battery can be thought of as an escalator that increases the potential energy of charges. The rating of a battery, or how much it can change the potential energy per unit charge, is measured in volts. This is why we have batteries that are 9 volts or 12 volts, for example. Changing the potential energy is achieved by doing work on the charges. So technically, a voltage of a battery gives the amount of work done per charge. And we call this the EMF of the battery. EMF stands for electromotive force, even though this isn't actually a force. We represent EMF with a script E similar to an epsilon. Since batteries do work and create this potential difference using chemical reactions, the EMF of a battery is the work done by these chemical reactions per unit charge, and we measure EMF in volts. We can think of EMF similar to voltage, but in this case it is a source voltage. An ideal battery will have a voltage or potential difference across its terminals that is equal to its EMF rating. This means that there is no loss in energy, and this will not be true while the charges are moving. But in most cases, the difference is small, so we often treat batteries as ideal. We'll look at how to treat non-ideal batteries later. Now that we have our voltage source that can do work to increase the energy of our charges, we can connect each terminal of the battery to one of the plates of our capacitor. The battery will increase the energy of charges from the bottom plate, leaving it more negative, and the positive charges will move to the top plate and be attracted to the bottom plate. While the capacitor is charging and charges are flowing, we call this flow of charge an electric current. We will look more at current soon, but for now we will focus on the capacitors after they have been fully charged and the current or flow of charge has stopped. While the capacitor is charging, the potential difference across the plates of the capacitor is less than the potential difference across the terminals of the battery. As more charge builds up on the capacitor plates, the potential difference increases. The capacitor will continue to charge until the potential difference on the capacitor plates is equal to the terminal voltage of the battery. At this point, the top plate and wire or conductor on top are all at equal potential with the positive terminal of the battery. The same is true for the bottom plate and bottom wire in the negative terminal. Now the charge on the plates is equal to the capacitance times the voltage across the capacitor, which again is now the same as the voltage across the battery. Now let's look at combining multiple capacitors. First, we'll look at two capacitors that are arranged in parallel. A parallel configuration looks like this. This represents a circuit formed by a battery and two capacitors, and we draw capacitors as two parallel lines of the same length. We know the capacitors are in parallel if we can go from one terminal of the battery to the other and only have to pass through one capacitor or the other. So there is this junction where the wire or conductor splits, and we can choose which capacitor to go through. We can draw circuits in different ways that make you think that two things are in parallel, so go ahead and practice thinking of things being in parallel using this rule of thumb. Now if we imagine charging these capacitors, charge will flow to both of them the same way it did in the single capacitor from before. This will continue until both the top capacitor plates and the wire conducting them are at an equal potential with the positive terminal, and the same for the bottom plates and the negative terminal. This means both capacitors will have the same voltage as the battery when they are fully charged, but each capacitor may have a different area and plate separation, so in general they have their own capacitance value. This means they will also have a different amount of charge on their plates when they reach the voltage of the battery. To describe the capacitance of the entire circuit when we have two capacitors in parallel, we will imagine creating a new circuit with only one capacitor, but it will behave the exact same way as our parallel circuit. Then we want to know the capacitance of this single capacitor if it is to be equivalent to the overall capacitance of our parallel circuit. We'll call this the equivalent capacitance. Our equivalent capacitor should be connected to an identical voltage source, so the same battery. This means it will also have the same voltage as the battery, just like C1 and C2 from the parallel circuit. The battery moved a total charge of Q1 plus Q2 from the negative side to the positive side of our parallel circuit. So the charge moved onto the plates of the equivalent capacitor should still equal this total amount of charge. Now we can write the equivalent capacitance as the total charge on this capacitor divided by the voltage across it. We can replace the charge with Q1 plus Q2. Then we can separate each of these terms and see that it is just equal to the capacitance of each individual capacitor. So if we want to find the equivalent capacitance of two capacitors arranged in parallel, we just need to add the individual capacitance values together. Since we're adding, the capacitance will always be larger by adding capacitors in parallel. Now let's look at capacitors arranged in series. This is when we must go through both capacitors on our way from one terminal of the battery to the other. We cannot go through one without going through the other as well. If we imagine charging these capacitors, the battery is still increasing the energy of charges from the bottom plate by bringing them to a higher potential. This will continue until the top plate of C1 is at the same potential as the positive terminal and the bottom plate of C2 is at the same potential as the negative terminal. In doing this, some amount of charge plus Q will build up on the top plate of C1, and minus Q will build up on the bottom plate of C2. The part of the circuit from the bottom plate of C1 to the top plate of C2 is isolated from the rest of the circuit because the plate separation is a physical gap. This means no charge can be removed from this region. It can only move around. The charge plus Q on the top of C1 and minus Q on the bottom of C2 will polarize this isolated region, pushing positive charges to the top of C2 and leaving the bottom plate of C1 negative. Again, here our two capacitors may have different geometries and thus different capacitance values, but we can see that they will have the same amount of charge on their plates once they are finished charging. Since they have the same amount of charge and different capacitances, they will also have different voltages. We only know that the top plate of C1 and the bottom plate of C2 must have the same potential difference as the battery terminals. So the total voltage across both capacitors must sum to the battery voltage. Now let's imagine our equivalent circuit and a single equivalent capacitor. Since there is only one capacitor, it will have the same voltage as the battery. To find the equivalent capacitance, instead of just writing the capacitance as the charge divided by the total voltage, we're going to flip both sides and write the reciprocal of equivalent capacitance. Doing this, we get 1 divided by the equivalent capacitance is equal to the sum of the voltages on C1 and C2 divided by the charge Q. The reason we wrote this as the reciprocal is because the sum would have been in the denominator, and we would not be able to separate the two terms. But here we can separate the terms in the numerator to get the voltage of capacitor 1 divided by the charge plus the voltage of capacitor 2 divided by the charge. Each of these is the reciprocal of each capacitance. So we get 1 over CEQ is equal to 1 over C1 plus 1 over C2. Be very careful here. This is not the same as adding the two capacitance values together. We must add the reciprocals, and then to get the equivalent capacitance, we need to invert this sum. Now let's write these more generally. In parallel, capacitance values add to increase the overall capacitance of the circuit. This applies to adding many capacitors in parallel, not just two. In series, we must be careful to add the reciprocals of capacitances, and then, after finding this sum, we invert to find the equivalent capacitance. It's very easy to forget to invert after adding, so watch out for this. Because capacitors in series add this way, placing capacitors in series will have the effect of always decreasing the overall capacitance of the circuit. The equivalent capacitance will be smaller than any of the individual capacitance values. Also, if you do the math for two capacitors in series, you find the result is equal to the product of the two capacitances divided by their sum. This is a quick way to add capacitors in series, and if you forget whether the product or the sum is on top, just look at the units. You need to end with units of farads. The product on top will give you farads squared, and when you divide by farads from the sum, you end up with the correct units. If you mix them up, your units will be 1 over farads. Now let's quickly look at the energy stored in a capacitor. The small change in potential energy achieved by the work of the battery is equal to the small charge that is moved by the battery times the voltage of the capacitor at that time. This is just the relationship between potential and potential energy. But in this case, we're looking at a small amount of charge dQ and a small amount of energy given to it du. The voltage across the capacitor at any point is equal to the charge on the plates divided by the capacitance. This is obtained by simply rearranging the definition of capacitance. Now that we know how to express a small amount of potential energy, we can get the total potential energy by integrating over the total charge that gets moved onto the capacitor. This gives the charge squared over 2 times the capacitance. We can also rewrite this by substituting charge equal to voltage over capacitance, which again is just rearranging the definition of capacitance. In this case, the energy is equal to 1/2 the capacitance times the voltage squared. So if we know the charge and either the capacitance or the voltage, we can find the total energy stored by the capacitor. We say this energy is stored in the electric field produced by the capacitor. Taking the final equation we got for the potential energy of the capacitor, we can do some substitutions. Earlier, we found that the capacitance only depends on the area and plate separation. We also know the voltage across the capacitor can be written as the electric field times the plate separation. Plugging both of these in and simplifying, we get this. Notice that the area times the plate separation gives you the volume between the plates where the electric field is. If we divide both sides by this volume, we can get an expression for the energy density, or energy per unit volume, which we'll write with a lowercase u instead of a capital U. Notice this equation only depends on the electric field and epsilon naught. The quantities that specify the shape of the capacitor are gone. And in fact, we can generalize this to be the energy density stored in any electric field. So that's it for this video on capacitance and capacitors, and I'll see you in the next one.